electron and the quarks are really made up of vibrating strings. And these can be linear vibrating strings, something like a violin string or something, or they can be circular vibrating strings. And the way you determine, what particle you're creating from this vibrating string has to do with the frequency of vibration of the string, whether it's linear or circular. So one other thing about this is that string theory supposedly is supposed to bridge the gap between quantum mechanics and general relativity, which has never been quite. You bring the really big together to the big really small, it doesn't quite work. And so string theory presumably is supposed to help bring those two areas of physics together. So here's my string theory model, sculpture. I created some linear strings in the middle here. So there are three different frequencies of linear strings here. They're kind of like different vibrational frequencies of a violin string or a piano string. And then there are circular strings. And so if you take this big circle here and think of the easiest mode of vibration would be for it to vibrate this way or vibrate this way. So these are the two modes of vibration of this sort of lowest frequency vibrating string. And then I created a whole bunch of others. This one has 4 different modes of vibration. So each one of these are the 2 different modes of vibration of this particular one. So I did 4, 6, 8, and 10. And so for artistic things, I've got different layers. So if this is the 10 mode vibration, then that's the 10, and that's the 10 in there. So I've got these different layers of vibration for artistic things. The other thing is that because of trying to bring together quantum mechanics and general relativity, I put a general relativity equation here and the uncertainty principle from quantum mechanics over here. So we've got 2 equations on here too. This is all copper wire, all soldered together, and then a base of basswood and cherry. So that's about all I know about string theory. Put that in here. Maxwell's demon. Maxwell is certainly best known for his equations of electromagnetism. But he was also a thinker, and he was trying to come up with a thought experiment of how it might violate the second law of thermodynamics. Well, the second law of thermodynamics could be described in terms of entropy or disorder, and so in any natural process, the entropy of the system or the disorder of the system will increase or remain constant. So Maxwell said, well, can I think of a way to violate this principle? So he said, suppose you had a box. You probably can't see this very well, but there's some blue balls and some red balls in there. They're supposed to represent the red ones hot molecules and blue ones cooler molecules. And there's a separation in the middle of the box and a trap door. The idea is if you put in a bunch of hot and cold molecules in here and leave the door open, after a long time it will be completely evenly distributed. So the demon says, well, I can do better than that. So the demon controls this little trap door here. And so the demon watches. If he sees a red one coming this way, he opens the door and lets it through. If he sees a blue one coming, he closes the door and doesn't let it through. So after watching for a long time, he lets all the red ones over here and all the blue ones over here. So it's more of an ordered system rather than a disordered system. So he's violated the second law of thermodynamics. So the demon's very happy. So you can see that he has a grin on his face. And he's holding up a sign that says, this is the equation for entropy, the integral of dq over t. The real equation is greater than or equal to 0. And of course the demon has got one that's it's going to decrease, or it's less than 0. So this is my Maxwell demon The reason the demon is a dragon is because my granddaughter, I carved something for each one of my grandkids. And so Ashley said, I want a dragon. So we got out a book of dragon pictures. And I thought she picked out this dragon. So I carved this dragon, and I showed it to Ashley, and she says, oh, Granddad, you carved the wrong dragon. So Ashley has a different dragon, and this guy has become Axel's demon. This is our Fermi surface. In metallic solids, the electrons can move around, and in the absence of some electric field or some field that causes them to do something special, they will tend to choose the position of lowest energy. And it turns out that the position of energy they choose is related to the crystalline symmetry of the particular material they're in. This is calcium, a Fermi surface of calcium. If you look up calcium in a crystallographic table, it's a body-centered cubic. And so that means that you have a cube with an atom on 8 corners, and then you have an atom in each of the faces. So there's 6 faces and 8 corners. So this one, if you think of this shape as the face, then there's the face here, face here, face here, face here, face here, face here. So those are the, if I got it held right, there we go. So we've got, these are the face-centered ones here, and top and bottom in the faces. And then these hexagonal shapes, if you look at them, are all pointing to the corners. So there are 8 of these hexagonal shapes and 6 of these shapes. This is an aluminum casting, and this is the most complicated casting I've ever done. And when we get to the end, I'll tell you exactly how we made this. And but it was a complicated way to do something. This one we could probably argue about. The de Broglie relationship says that something that has momentum has a wavelength, okay? So what if h was a big number, okay? So if we've got this sports car moving along at some speed and it has a mass, so it has a magnet momentum in this direction, then it should create waves, okay? Well, I'm not sure exactly how that would work, but I think if the wave front is coming towards you, you probably would see something that looks a lot like a car, or from the behind. But if you look at it from the side, you would see the waves. So I guess if you assumed a mass for this car and a velocity for this car, and assumed that this was the wavelength, you could calculate a value of h. Really, I think the best way to do this, if this is correct, would be, instead of making these little thin pieces of wood, actually be use a piece of thin metal. So if you create this with a bunch of thin metal, you'd see almost nothing when you look this way, but you'd see the thing coming at you here. I'm not sure this is completely right, but I thought it was an interesting thought experiment about the de Broglie wavelength and a hot rod. The Nobel Prize in Physics last year was for 2 British physicists who were working on something called graphene. To explain graphene, you can start by talking about graphite. We all know what graphite is. It's in your pencil lead, you grind it up and use it for lubricants. This is a piece of graphite, and it's not coming off of my shirt because I sprayed it with a clear finish. It's a real mess to carve, I can tell you that. You get covered with the graphite dust. But the top of it is carved. And the brass on top then shows the structure. Graphite is all carbon. And so each one of these intersections would be a carbon atom. And if you know about chemistry, the type of bonding is called sp2, hybrid orbitals. So it's a combination of s orbitals and p orbitals. And there are 3 of those, and then there's a p orbital perpendicular. So this forms a planar structure with a bunch of p orbitals sticking up. It's a very strong structure. And then in graphite, there are layers of these, and they're sort of oriented the way I've got them oriented here. I've got 3 planes. The bonds between the planes are fairly weak. So that's why it works so well as a lubricant, because these planes can move easily around across each other. Graphene is like one of these planes, 1 atom thick. So the guys that first started working on graphene took a block of graphite that wasn't sprayed, just regular graphite, put a piece of Scotch tape on it, and pulled it up. And they pull off 1 layer here. So you end up with 1 layer, 1 atom thick. So that's graphene. And graphene has some really unusual properties. It conducts electricity about as well as copper. It's a very good thermal conductor. It's transparent. It's 1 atom thick, so it's sort of a 2-dimensional solid. And it has some very unusual properties, and people are trying to make smaller transistors and all kind of things out of it. But, so graphene is sort of 1 layer of graphite. Let's see, you might turn out the light again. Let's try this. Let's see, why don't we unplug this one too while you're there. Tom Hunter and I and our wives were visiting in Spain. We went to a monastery in Spain, and in this church there were all these different places you could look at different kind of art. And I went into one of them, and there's this figure, face of Jesus up on the wall. And as I walked around, this face followed me. You know, I got down here and it looked down. I got up here and looked at it, looked over here and looked at me. And I was just fascinated me, and I thought, that's a sculpture that I've got to figure out how to do. So it took me a long time to figure it out, but this is, what you want to do is move your head around and see what happens. It's better if you walk around. The face is going to follow you no matter what you do. If I'm standing over here looking at it, he looks like he's looking at me. If John looks at it, he looks like he's looking at him. If you get down here, it looks like his head moves down. And so how does this work? Well, part of it has to do with your brain, which I don't know much about. But there's some part of your brain which takes this concave structure and makes it look convex, okay? That part I really can't explain. It has something to do with the neurology of the brain. But the reason it follows you is just pure old physics, reflection of the light. If I'm standing here and there's a light shining on my face and you're over here looking at me, you see this side of my face. But if that's a negative image like that, when you shine light, if you look at it from this side, you see this side of the face. So it looks like the face is turned in that direction, okay? That's why it follows you around. And you might look at that. If you can't move around much, it's kind of fun to walk all around, and get down low or get down high and whirl around and see. This is called a hollow face illusion. There are papers written about it. But anyway, I thought you'd like to see a hollow face illusion of our man Einstein. And I'll leave that on. So I told you I would say something about how we create these bronze things. So here's the bronze Einstein here, which is the picture up there. What you do is you make a rubber mold of the clay model. I started with the clay model. I made a rubber mold. Then you put wax in the mold. And then, so that's wax there. So that's stuff over there is wax. But you've got to get bronze into it, and you've got to have some vents so air and stuff can come out. So in addition to your wax face, that big piece of wax down the middle is called the sprue. That's where the bronze is going to go in, and the other 4 are called vents. That's where the air is going to come out and bronze will come out too if you overflow it. So what you do then is suspend that in something called, let's see there, investment. Investment is a mixture of different kinds of sand and plaster. So you mix all that up. You make this cylinder out of chicken wire and tar paper, and you use plaster to plaster to the floor. And then you mix all this stuff up, and while it's still fluid, you stick your wax down in, and you pour all this liquid in it. The liquid fills up to the top, and you hold it there until it hardens, which only takes a few minutes. Then you take the tar paper, well, you let it set overnight so it gets good and hard. You take the tar paper out, you turn it upside down, and you put it in a kiln. And you heat it up to about 500 degrees, and the wax will all melt out. So now you've got holes in there that were like what the wax was. And then you heat it up to about 1500 degrees, because what you're going to do is pour bronze in it at 1800 degrees. So you want this to be like a piece of rock. So you really heat it up hot and get all that sand to sort of feel like a piece of rock. So after you've melted all the wax and created your rock, you heat the bronze in a furnace in the floor and in a big old crucible, and it comes out, you know, red hot, and that's 1800 degrees. After you've melted all the wax, you bury these things in sand. You do that because if you don't get it out of the kiln and into the sand pretty quick, if it gets moisture in it and you pour hot molten bronze into it, it can crack or actually explode. So that's sort of a safety measure. So we pour our bronze into there, and then you let that sit overnight so everything's good and hard. Then you take a hatchet and you break that thing apart, and this is what you get over here. So everywhere you had wax, you have bronze now. So you've got to get an angle grinder or something and cut off all that extra bronze, which you recycle and use it for something else. But then you still have some work to do. This is where it came out. So it looks like he's got a wart problem. What happens at liquid investment, if you're not careful, and I wasn't careful, you get bubbles in there. And whenever there's a bubble, okay, there's a hollow space. That's going to fill up with bronze. So my Einstein had a lot of warts. So it took a lot of grinding and work to get him to look better, but that's what he looked like at the end. Wow. The other thing you have to do is put a patina on it, and if you just leave the bronze, you clean it all up and probably sandblast it and get it good and clean. But if you just leave it sitting out, it's going to turn green probably, which is probably not what you had in mind. So you put some kind of chemical on. You put different color chemicals to make it different colors. I mean, this one, if you compare these two, that's a very different color from this one. We used two different patinas on these two bronze sculptures. And then after you do that chemical stuff, you have to spray it. Either spray it with some clear finish or put a hot wax on it. But you've somehow got to preserve that finish and stop the chemical reaction from going on. When I made this one, I first of all thought I would make 8 of these hexagons and 6 of these squares and then bend it in this particular shape and weld it all together. But I realized that it would probably be impossible for me to make 8 of these exactly the same and 6 of these exactly the same. So we decided that we would make it a casting. So I first of all had to go to the wood lathe, and I created this on the wood lathe. You have to turn it on both sides and clean it up real good. And I created one of these on the wood lathe. And there you create these angles on here so they're going to fit together just right. And so then you make a mold, and so that you want to make these in wax. So you end up making 8 of these in wax, and 6 of these in wax. Then you got to put it all together, and sort of like this, and you do 8 of these and 6 of these and put it all together. Then you've got to put the vent and the sprue and all that stuff on it. It's a very complicated chunk of wax. But it turned out okay, and so that's the way I made this one. So it starting with a clay image of something. I started with a wooden image, and then went on from there. Well, I think you can tell I've been having a lot of fun, and be glad to answer questions or stay around for a while.
Before I entertain any question, I'd like to introduce another person who is accompanying Dr. Alexander, a good friend of ours, and he helped us very much while I was a graduate student there. And John Dept, our machine shop research instrument maker and supervisor of the machine shop, chief machinist from University of Alabama, Tuscaloosa, Tom Hunter, and who is accompanying Dr. Alexander. And he's also retired from there about the same time, Chet.
Yeah, about the same time,
about
exactly.
the same time. So they're still active, doing a lot of fun things other than what they used to do as a regular university staff, including the academic vice president of the university, now making sculptures. So there's a lot of fun things you can do, being a physicist or chemist or biologist, a lot of things there in the world. And this, as I mentioned in my introduction from our friend Wayne Cook, that this is what you have done, bridged between arts and science. So any question to Chester Alexander?
Yes, it's quite clear that you've spent a lot of money doing this, because that's not cheap to make bronze sculptures and aluminum sculptures and so on.
See, I took this sculpture course over a period of 5 years. I took 1 semester, and you usually do 4 sculptures per semester. So, for instance, for the bronze, I had to pay $45 a semester art fee. So I didn't pay for any of the bronze.
Oh, wow.
I mean, I bought the plywood, and I bought
okay.
this, and I bought this, and they had some chunks of graphite in the art department. This is 1/8" brass rod all soldered together. I think I had some cherry wood around, but they paid for the bronze. I found this cherry tree cut down somewhere.
Wow.
So I haven't spent a whole lot of money, but it's been a lot of fun. And
Maybe I can follow up on that. Is because if you did it by yourself at home, it would cost money, but you did through the class.
Well,
so this is kind of subsidized program. The class did help, and as you mentioned at one point that your fellow students who had been taking sculpture class, they also learned some physics.
well, they heard about physics.
They heard about physics.
They learned anything about it.
They
They heard
heard
about
about
physics.
physics.
And I heard a lot of art and art history, but I can't quote a whole lot of it. There's one interesting book here called Art and Physics, and it's about how changes in art and changes in physics occurred about the same period of time. Starting around 1900, there were a lot of sculptures became more abstract, and paintings became more abstract as we got into quantum mechanics. And so it's really an interesting parallel between changes in art and changes in sculpture or art and physics. And I got a lot of ideas out of that book. So that was fun. But I couldn't do the bronzes or the aluminum castings at home. You've got to have that furnace, you've got to have the kiln and all that. So if I hadn't been in the art department, I couldn't have done those. The wood I could have done, but the other I couldn't.
Any
I trust you got an A in the course.
What's that?
I trust you got an A in the course.
Yeah, I got an A. Best grades I've ever made. Better than my physics grade.
Yes, Don?
Question. I mean, I think there are future physicists students who are just starting out in physics. Would they be better off having a little more experience with the arts, sculpting things?
Well, there was an interesting talk at the university not too long ago about somebody who was in art saying that so many things now can be done by computers. Almost everything a lawyer does, except be in court, can be done. Wills and all that stuff can be done on the computer. so many things a doctor does could be done. You know, you look up, you know, what the diagnosis is, you put it in the computer tells you. There's so many things that you can do by computer now. What's important in physics or anything else is being creative, learning creative things. And he was saying, you know, I think people in business, he was talking mostly to business students, I think business students ought to take some art courses to help you with your creativity. So I think that's one thing you get out of all this. It's kind of fun to try to be creative. It helps you, you know, you want to be creative. I'd like to think I was creative in my physics research too, but I think the being creative in art and talking to art students is helpful.
What on earth is that bird?
Any more? Yeah, everyone.
So you mentioned that your sculpture on the shoulders of giants is on display at the physics department. Are your other sculptures on display, and how do
Yeah, this one hangs in the office, and there's a glass display case in the hall in physics, and there were, I think I had 6 of them. I kind of change them out from time to time, but almost all of these have been in that case at one time or another. This one won't fit, the string theory won't fit, that won't fit, this won't fit. A lot of them won't fit in the case. But there's one in the dean's office. Our dean is a big fan of Einstein. So I did another one of these, except that I put a collar on him, a shirt collar on him. And so that's hanging in our dean's office. And this one was over, we have a center for, seems like Magnetics Research Center. And so this one was displayed over in there. So I had about 7 or 8 on display at one time or another, and then there were a bunch of them around the house. I've never sold anything. Nobody's offered me any money, and I've never put a price on anything. Anyway, I have a lot of fun.
If no further questions, let's thank our speaker again.
Walk around and look
Yeah,
at it.
you can look at this.
Yeah, I think that's kind of fun.
Talking and talking. Let me move this one.
Yeah, it does.
During class, I just muted and that takes care of it.
Cherry, it's 1/4-inch cherry. And it bends so easily? No, it doesn't bend at all. This was a solid piece of cherry, and I used a scroll saw to cut it off. Then you got to sand it off.
Yeah.
You had to make sure.